Okay, so this is a basic, like an intro kinematics problem example, and it's from textbook Giancoli 5th edition. It says a car accelerates from 12 meters per second to 25 meters per second in 6.0 seconds. What was its acceleration? How far did it travel in this time? And assume a constant acceleration. All right, so reading through this question, I can see that it wants to know two pieces of information. I need to know what the acceleration is, and I need to know how far did it travel. All right, so those are the two things that I'm looking for. All right, so what I'm told in the problem is that the car starts out at 12 meters per second and gets up to 25 meters per second. Those are both meters per second, they're velocities. So the starting velocity is 12 meters per second. And the final velocity is 25 meters per second. And that occurs over a time of 6.0 seconds. The question asks what's the acceleration, and it also asks for how far does the car travel. So another way of saying how far something travels is how much did its position change, or how much displacement does it have. So that's going to be delta x. Okay. If I make a sketch of a v versus t graph of this situation, I have v in meters per second and t in seconds. The car starts out at 12 meters per second, and it gets up to 25 meters per second. It does say assume a constant acceleration. All right, so it's going to get up to 25 meters per second up here, and that occurs at 6 seconds. So that would be a sketch of the situation. Okay, now we know our principal kinematic equations are these. Vf equals Vo plus At, delta x equals Vot plus a half At squared, and Vf squared equals Vo squared plus 2a delta x. First, I'm going to find the acceleration. So I'm looking at my three equations, and I recognize that the first equation there can allow me to solve for a because I know Vf, Vo, and t. So I'm going to write that out. Vf is Vo plus At. I'm going to solve that for acceleration. So subtract Vo from both sides and divide by t. This should be familiar, Vf minus Vo over t. That's change in velocity over time. It's a definition of acceleration. All right, so we have 25 meters per second as the final velocity. We have 12 meters per second as the original velocity. We have 6 seconds as the time. So if I plug in to my calculator, I get 2.17 meters per second squared. So the acceleration, 2.17 meters per second squared. It also asks for how far. So now that I know the acceleration, I could use either the second or the third equation. But if I think about it, it's going to be easier to use the second one because it's already solved for delta x, whereas the third one I'd have to manipulate. So I'm going to use the second equation, delta x is Vot plus a half at squared. I'm going to use this to solve for delta x. So I have delta x equals Vo is 12. The time is 6 seconds. It's 1/2. Acceleration 2.17 meters per second squared from the earlier part. 6 seconds. Be careful here, only that it gets squared. All right, so I'm going to break this into 2 steps just for this first one. So 12 times 6 is 72. That goes here. And 1/2 times 2.17 times 6 squared gives me 39.06. So together, that gives me delta x equals 111.06 meters. And it was given as two significant figures. So if we round to 2 sig figs, our answer here is 110 meters. And our answer here for sig figs, 2.2 meters per second squared. So going through the process, read the problem carefully, look for what you're trying to find, make a sketch of V versus T, then set up your equations, and once you have the variable solved for, plug in the numbers you need to solve the problem.